Let's just talk a little bit about what the goal of Newton's law really is. So the Newton's law that everyone who walks around is familiar with is that F equals ma. It's sort of an equation that demonstrates, maybe you know something about physics, force is mass times acceleration, and however you want to interpret it is just fine. We are dispensing with this form just a bit in this case here, in this class, and we're saying instead that A is rather the force over m. It's the same law, just rearranged algebraically, but this form is much more convenient and conducive for problem solving. But we're even dispensing with this just a bit because we recognize there can be multiple forces on an object acting in multiple directions. So really what we want is that the vector A is the sum of the vector force divided by m. This is sort of the version of Newton's law here that we're most focusing on in this class here. Now, what is the goal of this law? How does it help us? Well, remember that the goal of elementary physics and this mechanics here is back to this idea of predicting motion. We can think of many examples where that's actually worked for us, sending rockets to the moon, or understanding how brakes will stop a car, or a football in flight, or making an airplane fly safely and properly in the air. Physics has done quite a good job in predicting motion, and the way we predict motion is with the equations that we learned very early on in the class, something like this. Plus 1/2 a times delta t squared, and v will be v naught plus a times delta t. These two equations here are the predictors of all motion here. And notice also, or not notice, but remember that there's also a version of this for y. There's one that says y is y0 plus v0 delta t plus 1/2 a delta t squared. There's also one for the velocity in y, v naught plus a times delta t. We have these two equations which allow us to predict the motion throughout something's sort of lifetime. And if we wanted to get very careful about it, since we're being very specific about the x and y, this would be a v naught x in here, now it would be an ax. This would be a v naught x, now it would be an ax. This would be a v naught y, now it would be an ay. This would be a v naught y, now it would be an ay. So we get very specific about the variables to get them all dressed up. But let's look once again at what they have, what they tell us. In particular, this equation right here, x and y are the position of the object. So if you have an object like a ball like this, and you want to know where it was in space, whether you're going to plot it on a computer or just understand where it would exist in the world, this point right here is an xy point. And you can imagine just drawing that on a big Cartesian coordinate system so you know where the position of this object is. And that's the real power of physics, knowing where the position of an object is going to exist. And notice an xy point, well, that exactly comes from these two xy equations right here. Here's x and y right here. The equations predict the horizontal and vertical position of the object, so you may go understand where it's going to be. The y position, of course, might tell you how high it is off the ground. The x position might tell you how far over it is, say from the edge of the building or whatever your reference point is, but the equations give you the x and y. The next thing that you might want to know is, well, what is the speed of the thing? What does the velocity vector look like? Where is it going to be a small time in the future? Well, you look back at the equations, so we can dress them up even more. This is actually going to be a vx in here. This is actually going to be a vy in here. And now, if you know where the position of the object is going to be, which we do, now you can draw the velocity components on there. You can actually draw now, here is a v sub x, and here is a v sub y. And the vx and the v sub y, once again, they come from these equations directly here. That's what they're there for. That's what they do for us. Now, if you wanted the full velocity vector, well, if these are the legs, you can always draw the vector just by completing the hypotenuse in there. There's the full velocity or the speed of the object. So off you go. And there's even more you can do like that. If you want to know what the angle of the velocity vector was, say, you know, what the pitch of the vector is, if you will, you can say that theta in there. And as we learned before, theta is always involved with the inverse tangent. The inverse tangent, Vx over Vy, all of these nice things that allow us to describe the motion of the object come from sort of what's on this whiteboard here. Now, here's the purpose of Newton's law. The goals of Newton's law are as follows here. If you look at these equations here, what do they consist of? Well, if you want to know the new horizontal and vertical position of an object here, you certainly need to know its current position, x naught and y naught. And you need to know its current velocity, v naught x and v naught y. And you have to have some time interval, which you are free to choose. So if you want to know where this thing is going to be a bit later in the future, there'll be another circle right here. Let a little bit of delta t go by, and that's certainly part of the analysis or part of the consideration. How long in the future do you want to predict its motion? But now, here's the goal of Newton's law, the crux of the video here. Look at this term right here, ax, and ay. What is absolutely critical in these equations to successfully do these predictions and to understand where an object is and how fast it's going is to know its acceleration, its x acceleration and its y acceleration. That is very important to know and very key in what's going on here. So if you just sort of move the board down and look at the notes, where are those accelerations going to come from? They come here from Newton's law. The vector acceleration, the sum of the vector forces divided by m. And we know we can break this equation up into two because it's a vector equation to be the sum of the x forces divided by m. And we know the y acceleration will be the sum of the y forces divided by m. We know we can always break the vector form up into these two, ax and ay, sum of the forces divided by m. And so when we have the two a's, the ax and the ay, we can drop down to our equations and go, okay, I have ax, I have ay. Now I am free to do all this motion prediction business that we discussed. So that's really what the goal of Newton's law is. The goal here is to give us the accelerations. And once we have the accelerations, then we can make our prediction or do our mapping about the motion, but we must have those accelerations. And notice in particular what the accelerations depend on. So you can certainly get the equations by summing the forces and dividing by the mass. So where are these forces going to come from? Well, those are the forces now that come from our list, which we sort of described and are working on in a different video. But for instance, these forces here can be weight, or tension, or friction, all of these forces that we're talking about here, or the centripetal force. It just goes on and on. It can be a force that comes from a spring. It can be the sliding force, which is what causes things to roll down hills. It can be the normal force. And the list really goes on and on. This is probably most of the ones that we'll deal in the class, but that's the point about Newton's laws. These are the things that you would actually observe the object to be sort of being impacted by. It can be impacted by its weight. It can be connected to a rope. It can experience some friction as it goes over a rough surface. It can be traveling in a circle, attached to a spring. It can be rolling down a hill. It can be sitting on a surface. These are all the forces that you'd expect to sort of see in the everyday world, an object to be sort of affected by. And Newton's law says if you can identify these forces to the point where you can plug them into these sums, you can get the accelerations, then you can make your predictions about motion. And so that's the goal of Newton's laws, is to go from the forces, the everyday things you see, to the accelerations, back to the kinematics so you can predict what the motion of the object is going to look like.